So when we were looking at the idea of free fall on the side of the page where we were dropping the object from rest, we had a very visual representation of the object getting faster and faster, traveling this distance, then more distance, then more distance, then more distance in equal time intervals, showing us getting faster. We also showed it by comparing the velocities and drawing arrows to show it going at 9.8 meters per second, then twice that, then 3 times that, then 4 times that. Let's look at one more way of making comparisons. Look at the numbers here. So for example, in the first second, you can calculate that the object falls 4.9 meters. And then if you're going from 0 seconds to 2 seconds, it falls 19.6 meters. And that's shown here by the picture. But now let's look at the ratio of the distances. So break out your calculator and just find the ratio of 19.6 to 4.9. And you should get its ratio of 4. So in 1 second, it falls a certain distance, and in 2 seconds, it falls 4 times as far. Why does that happen? Well, it can be linked to the equation, and the equation is right here. Let's focus on this second version here, where I'm going to rewrite it as delta y equals v naught t plus half at squared. I'm calling it delta y because, again, it's going vertically. And on this side of the page, remember, we had the object being dropped from rest. Anything times 0 is 0, so this just reduces to delta y equals 1 half at squared. This is not a new equation. This is just the long displacement equation if v naught equals 0. So let's see what happens here if we change the time. I'm not going to put numbers in. We're just going to see what happens if we, for example, double the time. So remember, in 1 second, it falls 4.9, but now we're going to 2 seconds. We have effectively doubled the time from 1 second to 2 seconds. So you can call this delta y new. That's 1 half a, and then we're just doubling the time. So it's 2t instead of t. So from an algebraic standpoint, we know if this side is multiplied by 2, that means that this side should be multiplied by 2 as well. So this says that if the time is doubled, the displacement should be doubled as well. But wait, that's not what happened, right? If you take the ratio of 19.6 to 4.9, that was a ratio of 4. It went 4 times the distance when the time was doubled, not twice the distance as the algebra appears to show here. Well, you might see we kind of messed up, because in the equation, the time is squared, and we need to do something with that exponent as it relates to the factor of 2, because whatever time you put in there has to get squared. So here's what we really should have done. We should have put parentheses around this. When you put parentheses around this, it's saying that you have to square anything inside the parentheses, meaning that if you're putting in double the time, you have to square that new time. So now, if we think about this from an algebraic standpoint, the t gets squared, but so does the 2. And of course, 2 squared is 4. That means that this is 4 times 1 half at squared. You can imagine taking the 2, squaring it as a factor of 4, pulling a 4 to the outside, leaving 1 half at squared inside. 1 half at squared was the distance it fell in the original time, which means that the new distance it falls is 4 times the old distance. And that's what we found, that if it falls about 4.9 meters in 1 second, it falls 4 times that distance if we double that time. What if, for example, we compare the distance it falls in 2 seconds to the distance it falls in 4 seconds, again, doubling the time. So here, let's take the ratio of 78.4 to 19.6. Again, break out your calculator and do that. And what do you find? Yeah, it's a ratio of 4 again. So if the original time, for example, is 2 seconds, it falls 19.6. And we double that to 4 seconds, it falls 78.4. When we double the time, we quadruple the distance. And that's what's being shown here. Doubling the time, but the time gets squared. 2 squared is 4. Pull that factor of 4 to the outside. That leaves the original distance, which means the new distance is 4 times whatever it was before. What if instead you were to triple the time? What do you think would happen? Well, let's compare. In 1 second, it falls 4.9 meters. In 3 seconds, it falls 44.1. So now take the ratio of 44.1 to 4.9. What does your calculator tell you? It's 9 times the distance. So now you want to think, if we put a time in here and we triple that time, that would be 3t in parentheses squared. 3 squared is 9. And so you see, you put the factor in here, and then because t is squared, you square that factor. So it's this general idea that we want to compare one situation to the other. You don't even have to put numbers in. You put the extra factor in to the equation. You manipulate it according to the equation. For example, here the time is squared, so the extra factor gets squared. You pull that extra factor to the outside, that leaves behind the original value. So if it's 2, 2 squared is 4. If it's 3, 3 squared is 9. What if the time were half as much? Well, you'd be squaring 1/2. Squaring 1/2 gets you 1/4. So if it's half the time, it gets 1/4 the distance. So again, the idea is you put the extra factor into the equation, manipulate it according to whatever the equation tells you to do, pull the extra factor to the outside, and that should leave behind what the original was. Let's see if we can apply the same idea to one of our homework problems. Focus on concepts number 13 out of Cutnell and Johnson. So here we have the two racehorses. They start from rest because, of course, if they weren't, it wouldn't be a very fair race. And they have a constant acceleration, but it says that the same elapsed time, Silver Bullet runs 1.2 times faster than Shotgun. We want to know what their ratio of accelerations is, what the relationship is. Now, you may have a gut instinct as to what this is going to be, but it's not just about going with our gut. We need to go with the equations. So we need an equation that relates the time and the distance and the acceleration, and we know they start from rest. We know v0 could be in there as well. So the equation relating all those terms would be our long displacement equation, delta x equals v0 t plus half at squared. We have the distance, we have the initial speed, we got the time, we got the acceleration. And since they both start from rest, again, v0 is 0, anything times 0 is 0, so this reduces to delta x equals half at squared. Now, the information here tells us that one horse runs 1.2 times farther than the other. That means that delta x is 1.2 times as much. So I'm going to set it up like this. So it's 1.2 times of delta x equals 1/2. I'm leaving a blank in here to see what factor would go in for acceleration, and time is not changed at all because it says in the same elapsed time. So here we're not changing time at all. We're just going to compare the distance to the acceleration. So now we're thinking about what would make this a mathematically correct statement. If the left-hand side is multiplied by 1.2, the right-hand side also has to be multiplied by 1.2. Again, I'm using parentheses to sort of group this extra factor with the term that's changing, right? The acceleration that's changing, so we group the 1.2 and the a together with parentheses. And so we see that to travel 1.2 times the distance, it has to have 1.2 times the acceleration if the time is the same. So in this case, our correct answer is letter D. The acceleration of Silver Bullet is 1.2 times the acceleration of Shotgun. This is a little bit different from the previous example where we had to do something and square it. But that's because it's the time that gets squared in the equation, but we're not changing the time. They both run for the same elapsed time. In this case, it's the acceleration that changes, and in the original equation, acceleration is not raised to any exponent, so we don't have to worry about raising this extra factor to any exponent either.